So I think it's time to start, guys. Good morning, everybody. Not everybody is here. I've seen some people queuing to get a coffee, but we need to keep up with the timing. So let me just tell you what we're going to do today. Basically, this morning, I'll continue saying something about electron-phonon physics, general theory, and then we will have basically a lecture from Xavier Gons on temperature-dependent band structures, and that is linked with the introduction to Abinit and hands-on sessions this afternoon with Abinit. Clearly, Abinit is a different code than Quantum-Espresso, and we were wondering whether it would be a good idea to mix two codes, and we decided that yes, that should be a good idea because it's going to give you, different tools to attack different problems. So it's going to be a little bit of a broader, tool set at the end of the workshop. Couple of technical announcements. At 11, basically after the second lecture, we are going to take the group photo, and so at the very beginning of the coffee break. So we just walk upstairs to where we have coffee usually, and we will have the photo on the terrace. Okay, so that's easy. And then the other thing is that this afternoon, so tonight there's going to be a reception at 7:30. Clearly everybody is welcome, and we hope we're going to all see you all there. And I guess now it's time to get started. Okay, so in the title of this lecture is Electron-phonon effects in ARPES and IXS. So ARPES is angle resolved photoelectron spectroscopy. I mentioned that yesterday, and IXS is inelastic X-ray scattering. This is a kind of a bit of a narrow title. Really, what I wanted to do today is to continue on the general theory of electron-phonon interactions, but this time shifting the focus from the electrons to the phonons. Okay. And IXS is there because one can do very nice measurements of, essentially phonon density of states using and phonon spectral functions using these tools. So in the lecture is organized in this way. I wanted to tell you basically, something which is somewhat a continuation of yesterday's discussion. So it's going to be about 3 slides where I'm going to show you some other things that one could do with the electron-phonon self-energy that we have not seen yesterday, but that are in the tutorials. And then that's still also do with the electrons, and then we'll move to phonons, okay? And for phonons, we're going to discuss the phonon Green's functions in the same way we did yesterday, the electron Green's function. Most importantly, we're going to try to understand how the language of Green functions can be made compatible with the calculations that we do in density functional perturbation theory. This basically will lead to introducing non-adiabatic phonon dispersions and phonon lifetimes. So during the tutorials, you've been calculating something called the gamma, the phonon lifetime, so the phonon broadening. So here we're going to do the theory of that quantity, see how that quantity emerged from these concepts. And then I will tell you just a couple of things about the electron-phonon matrix elements, but it's going to be very brief. So just for those who have never seen a slide like that on ARPES, I want to explain in very simple terms. Basically, ARPES is a way to measure essentially band structures, okay, directly. And the way people do that is to shine light on a sample. So if your photon energy is larger than the work function, that means that you can extract electrons, okay? So when you extract an electron and that comes out, what you can do is to try to detect it. So to use an analyzer, which is essentially a charged, 2 charged plates, deflecting a trajectory and send the electrons on a detector. And on the detector, you can tell from the position that the particle hits at the detector, you can tell the energy at which the electron was, that the electron had when it exited the sample, and also the angle. And from these 2 quantities, people can extract, essentially reconstruct the electronic band structures inside the sample. So this is essentially the best tool that is available today to measure band structures, and it's very powerful. So the light source is typically either a laser in a lab, in a benchtop, or a synchrotron source. With these things, one can do many pretty measurements. So yesterday, we discussed the example of, for example, the kink in magnesium diboride. So the fact that dispersions, due to electron-phonon interactions, they bend near the Fermi level. There was an electron-phonon effect. And now I want to just discuss another option that has been observed recently, recently, the past 5 years, let's say, in experiments. And before going there, I just want to show what could happen using a very simple example. So this is basically the same example that I gave you yesterday. So I told you if you consider an electron gas, so parabolic dispersions, okay, and this would be, the yellow line would be, one segment of this parabolic dispersion. You have to imagine a parabola which goes down all the way and then up. So the Fermi energy is very large. So this is the characteristic phonon energy, and we say that the electron-phonon interaction, if you include it, it kind of bends the bands here, and then it goes back to the standard non-interacting dispersions. So that's what we discussed yesterday. We've seen examples from experiment, MGB2, graphene related systems, from calculations, and so on. Now, there is another interesting thing that could happen in this case without changing anything, without changing the physics, without changing the self-energy. So what could happen is that the Fermi energy is not very large, meaning that in this case, suppose, let's imagine this is MGB2, so the Fermi energy would be maybe, would be maybe the bandwidth would be maybe 5 electron volts, and the phonon energy would be of the order of 100 millivolts. So these two numbers are very different. But imagine a situation where the Fermi energy is comparable to the phonon energy. So what is going to happen is that this object will kind of happen on the same energy scale as the bandwidth. And if you do the same exercise, you get something quite different. So instead of having a bending of the bands, what happens is that the yellow bands get kind of folded back. So the kink here would merge with the other kink. So you have a new dispersion, which in a sense is still a parabola, but has a much heavier mass. But also you have another object here, which is essentially something splitting off the main bands, okay? So let's say a satellite. So this model is too crude to do anything predictive, but it just gives us an idea that if you can engineer materials where the Fermi energy is very small, you can get something quite strange happening. And in practice, there are some systems where you can do that. So people have been doing some work since 2013 on transition metal oxides. And the reason being that these oxides are insulators, but if you start removing oxygen by creating vacancies, you can actually end up n-doping the system. So you inject electrons. So in practice, what people have been doing is to populate the conduction band of some oxides with a few electrons. And by doing that and tuning the vacancy concentration, you can obtain Fermi levels which are the order of something between 50 and 300 millivolts. So actually, we are in the energy range of phonons. And people have been observing things like this in ARPES spectra. So some main bands and then some satellites. So let me just give you an example of that. So this is what I showed you already twice in the previous lectures. So in this case, this is strontium titanate. So in ARPES, you observe this kind of conduction band, but also some replicas. So there's first satellite, second satellite, third satellite. So this is another manifestation of electron-phonon effect, which is the friend of this kind of kink, but is slightly different, okay? And these things were difficult to see a few years ago, but now are quite accessible. I just want to tell you that if you want to try to compute these things, unfortunately, the simple kind of what we said yesterday is not enough. What we did yesterday basically is to write down an expression for the self-energy, which was this object, after neglecting the vertex. And what I told you is that to do the calculation in practice, so to have the expression which we have implemented in EPW, we replace the Green's function by the Green's function by essentially a Green's function calculated in density functional theory. So we use Kohn-Sham eigenvalues and eigenfunctions. And we use the phonons from density functional perturbation theory. So that's an approximation because the Green's function should be the fully interacting Green's function. So if you don't do the approximation, it turns out that this term will lead to some satellites, okay? So that is possible. However, the position of the satellite, so the energy of the satellite is a little bit wrong. So you don't match experiments exactly. And that has to do with the fact that we are taking out this vertex, okay? So this is a bit of a technical discussion which is currently ongoing in the literature, but very simply speaking, the point is that this vertex contains some interaction terms, so essentially a ladder of phonon emission absorption events, which you need to adapt and you need to include in your calculation, otherwise you're not going to get the right physics, okay? So this is something which has a name, it's called the cumulant expansion. I will not tell you too much about it because in the next lecture, there will be a discussion about this method. So the only thing I would like to tell you is that in practice, the way operationally we do this is to calculate the self-energy that you already have seen yesterday a little bit within the approximation that we discussed yesterday. And then we somewhat manipulate the self-energy using a very simple kind of algorithm. And this yields a new spectral function which incorporates the satellites. So the only thing I'm trying to say is that when you need to go to this kind of more complicated stories, it doesn't mean that the calculations become horrendous. Actually, the complexity of the calculation is the same as what we did yesterday. It just requires some extra manipulation, okay? So if you want to look at the references, I've wrote them down so you will find them online. But again, this will be discussed in more detail in the next lecture. So this is just an example putting here because this is was calculated by Carla. She ran the first tutorial yesterday. So basically, this is a satellite in titanium dioxide, and this is her calculation where you see basically the conduction band, the first satellite, the second satellite, and if you try to reconstruct the bands, you see this kind of replicas. So these things are becoming quite popular now. There are many experiments seeing these things. And there is a bit of an interest in the community trying to understand these features and whether one could use them, okay? So this was just to tell you that you may find this kind of experiments or discussions in the literature, and it's something that we can now calculate. It requires a little bit more effort than what we've seen yesterday, but it's not too difficult. Now, let me just stop with the electrons. And you remember yesterday I gave you this kind of diagram where I say that the electron-phonon problem is a symmetric problem. So electrons are affected by phonons, but also affect phonons. And yesterday we looked at how the vibrations change, for example, the back structures and things like that. So today what I want to do is to show you that actually that the electrons can have quite an important effect on lattice vibrations, okay? So the theory is the same as the one that we have discussed yesterday. So there is nothing new. We just need to focus on the consequences of that theory for the phonons. So the many-body Hamiltonian is the same that we introduced yesterday. The techniques of Green's functions and quantum field theory are exactly the same. So what we're going to do now is just see how those things tell us something about phonons. So yesterday I had to introduce something called the phonon Green's function or displacement correlation function. So that was needed to obtain this wiggle in the diagrams, the phonon self-energy, that we need to calculate electron self-energies. It turns out that that quantity is the key quantity that we need to evaluate if we want to study vibrational excitations, okay? So if you remember, one of the things we found yesterday is that the importance of the Green's functions for electrons is the fact that if you look at the poles, you get the excitation energies of the system, okay? So in the same way, if you can obtain a phonon Green's function, the poles of this phonon Green's function will give you the vibrational excitations of the system. So in a sense, the calculating phonon Green's functions is a way to obtain the phonon density of states. So now you may think, okay, but I can do the phonon density of states with the FPT. That's true, but that actually it's an approximation, and we will see how that approximation comes about, okay? So in the most general framework, we need to look at the Green's function. So the definition of the Green's function, in the case of phonons, is a bit different from electrons. So in electrons, we have a field operator, so a field creation operator or destruction operator, which depends on a continuous variable, so where you are where you are looking at in space. In the case of vibrations, we have discrete atoms in the system, so the dynamical variable is the displacement of each atom. So in practice, what do we do is to have a displacement creation operator, which is essentially the displacement of an atom, acting on the ground state, okay? That creates a new state, which is the ground state plus a displaced atom at a given time. And that is sandwiched with another state, which is the ground state with a displacement in another atom and at another time, okay? So this is really, if you take the square modulus of that, that's the probability that if you move an atom at some time, you will find another atom displaced somewhere else at another time, okay? That's essentially the propagation of an atomic displacement. It's identical to what we do for electrons, but in this case, no, we are discrete ions, so it's a little bit different, the notation. And what you can see here is that, so if we have, we are in 3 dimensions, the displacements are essentially contain 3 Cartesian coordinates. So this is a 3 by 3 matrix because this is delta tau transpose. So they essentially generate a 3 by 3 matrix, okay? And there is one such matrix for each pair of atoms, okay? So there are 3 by 3 matrices times number of atoms times number of atoms. That's the kind of information we need to look for. Now, when you want to look for the excitations of this object, essentially what you are saying is that we need to evaluate this Green's function. And the usual tool for evaluating Green's function is to start from the equation of motion for the field operators, okay? So that's the same thing that we did yesterday for electrons. In the case of electrons, we had the Heisenberg equation of motion for the field creation operator. So we had psi dagger here and psi dagger here. The same equation is valid for the phonon, so the displacement creation operator. So that's the starting point of the discussion. And the Hamiltonian is exactly the same Hamiltonian we have written yesterday. So if you go back to the lectures around the middle of the kind of the slides, you will find the definition of the Hamiltonian. So now this is something which is interesting, but it's quite far from physical intuition in the sense that when we discuss phonons, we are very used to something discussing things like forces and acceleration. So we really like to think of the dynamics of nuclei using the Newton's equation, really, like force equal mass acceleration. So the acceleration is a second-order derivative with respect to time, and this is a first-order derivative, so that's not really the same. But I can go towards like a Newton's-like equation, for example, by just taking the derivative of this object. So if I take the derivative of that, here I end up with a second derivative. This is time independent, so I have a derivative of this object, but the derivative of this object is given by this equation already. So well, I'm going to end up with a second derivative equal a commutator where there is another commutator inside, okay? So it's just 2 seconds to do the maths. So this is essentially an equation where I also added the mass on the left and on the right. And you can see that on the left, I have mass times acceleration. I mean, a many-body version of the acceleration of an atom. And on the right, I have a double commutator. If you do the maths, I mean, if you do just a back-of-the-envelope evaluation, you realize that this actually has precisely the dimensions of a force. So this is essentially a many-body force acting on the nuclei. And this is, the closest thing to the Newton's equation we can get starting from quantum field theory, basically. So the trick here is to try to now evaluate the time evolution of this object in such a way as to obtain then the time evolution of the Green's function. That's really the goal. I'm not going to give you the steps because it's going to take quite a long time. It's actually not that trivial, but I will give you a reference at the end where the maths are done. I would like just to give you the final answer. Essentially, this leads to a time evolution of the Green's function, which has the following shape. It's the identity here minus an object which is the product of two things. The first one is called the self-energy of the phonon, and the second one is, again, the Green's function. So that's basically this thing. Clearly, this is just a formal thing. I did not prove it, but it's useful to start having this equation to see what happens. The phonon self-energy, if you do this kind of derivations, takes a very simple form. I mean, it's ugly to look at, but it has a very nice physical meaning, and I'm going to show it to you now. So that's basically what you obtain as phonon self-energy if you do the maths, thoroughly. And even though it looks ugly, I'm going to convince you that actually it's very, very simple and it's very appealing in terms of concept. So what we are looking at here, that if you ignore everything on the left, so this bit here is essentially an electrostatic interaction between pairs of nuclei, let's say, okay? So we are really talking about so if we neglect this part, we are talking about an electrostatic energy and a second derivative of this energy, okay? So if you remember the talk of Stefano De Gironcoli regarding DFPT, he was telling us that you get phonons by taking second derivatives of the DFT total energy, okay? Derivatives with respect to displacements. So this is some kind of energy, and you take second derivatives. So this starts looking like what he was talking about. The complexity is that we don't have just the electrostatic energy between two nuclei, and that's it. There is also the dielectric matrix of the electrons, okay? So that's the full screening matrix of the electrons, meaning that is the charge, essentially is the dielectric function that you obtain by considering all many-body interactions in the systems and by considering only the electrons, so without the phonons. So what this means that if I look at this interaction, so this has a dummy variable, which is the position. This has also a dummy variable, which is a position, and there is an integral here. So what this really means, actually, is that I'm not looking at the interaction between two nuclei in the middle of nowhere. I'm looking at the electrostatic interaction between two nuclei immersed in a system where there are other electrons, okay? So this dielectric matrix is saying that they don't see the full charge of each other, but they are screened by the presence of the electrons, okay? And the screening is a little bit complicated because depends on two variables. It's a non-local screening, and there is a frequency dependence. So this screening is also frequency dependent, okay? So that's basically just an energy, and I take the second derivatives. So in a way, this is the analog, as we will see, of the FPT. And I just need to tell you that I slightly simplified the story. So if you do the math, there is an extra term here, which is a bit nasty, and I don't want to discuss it today. Essentially, it's a term which cancels the force that an atom exerts on itself, okay? So these things happen in quantum field theory. They are well known, so they are not harmful. We just need to do the maths correctly. But this is something which is a bit technical, so we skip it. So the bottom line of the story is that if you want to study the phonon dynamics, essentially, you end up with a phonon self-energy, and this is essentially the second derivative of an electrostatic interaction screened by the electronic dielectric matrix, okay? Now, if you want to remember the story about the harmonic oscillator, if you have a spring, the total energy is half spring constant displacement square. So you take the second derivative and you get the spring constant. So if you imagine that, maybe I'm going to go here. If you imagine that this is the total energy, okay, by taking second derivatives here, you get the spring constant. So this object really is the many-body spring constant, which connects all the atoms with each other. But,
so at this level of theory, is it a big assumption to assume that you just use kappa as a discrete coordinate? Because I remember in previous lectures, you also mentioned that sometimes it's important to consider ion as not just a point constant.
that's correct.
But here, you just use kappa as a discrete coordinate.
So let's forget the electrons for a second, okay? So if you have the nuclear wave function, okay? Instead of writing, let's say, the nuclear wave function as a function of x, so that's basically a broad wave function. That's what you're talking about. What we are basically saying is that if you can identify the center, I rewrite that as x naught plus a displacement. So actually, I'm just saying that this delta tau is this displacement, actually. So we're not losing information on the wave function. It's all there in the formalism. So there is no assumption that the nucleus is a classical particle, actually. We are just saying that if you describe, so when you look at your dynamical variables, basically the dynamical variables are the field operator for the electron and the displacement operators for the nuclei. So this is essentially a complete mapping of the complete many-body wave function electrons and phonons into a second quantized formalism. Okay, so we're just saying that we are concentrating on this object. But let's say when you take this, when you look at this definition, okay, here, when you have these brackets, that means that you are looking at how this operator acts on the complete many-body ground state. So it includes the fact you're talking about, okay? Okay, so just to continue on that, I just want to rearrange a little bit the matrices. So if you remember, I told you these are 3 by 3 matrices, but there is one for each pair of atoms. So that's a bit messy to work with. So it's convenient to do some bookkeeping and essentially place all the matrices for different atoms, like in a block matrix. So this is for 3 by 3 Cartesian coordinates, atom 1 and 1. atom 1 and 2, atom 1 and n, and so on. So that's just a rearrangement of the matrix. That's because things will be easier like that. So you can do the same thing for the self-energy, and you can define a new matrix which contains all the masses along the diagonal. That's bookkeeping, okay? The reason why I'm doing that is that if I rewrite the equation on the previous slide using this kind of restructuring of the matrices, I get a very nice equation. The only other step I did is that the second derivative in time has been transformed in Fourier space, and therefore it gives omega square as a prefactor. So really, this is the key equation to study nuclear dynamics. So it's the matrix of the masses, omega square, the phonon-Green function equal identity plus phonon self-energy and phonon-Green function, okay? So that's pretty much it. The complexity in this story is clearly to try to find to immerse this equation and find the vibrational frequencies out of that, okay? And clearly, the most important point would be to try to calculate the phonon-Green function. So if I immerse this, so what I can do is to essentially bring this thing on the left and factor out the Green's function and then immerse both sides. Essentially, the formal solution is very simple. The phonon-Green function is equal to the inverse of this matrix of masses times omega squared minus the phonon self-energy. So that's pretty much it. So if you want, this is actually the exact solution of the nuclear dynamics in the harmonic approximation. So it's exact many-body solution, okay? There is not much more than that. Problem is that this is just a formal solution. It doesn't give us actual numbers. So one has to now work out how to get actual numbers for this, from this thing. And if you have something like that, which is essentially, if you forget the matrices is 1 divided this object, we can look at the zeros of this object to get the resonances, okay? The little issue is that this is not just a scalar. So to look at the zeros of that, we are talking about the zeros of a matrix equation. So the easy way to proceed is to essentially diagonalize this self-energy matrix and then try to look at the zeros via the eigenvalues. So what people can do is the following. I try to diagonalize this matrix. I find some eigenvalues, but the eigenvalues depend parametrically on the frequency. So what I need to do to find the resonances is to solve a nonlinear equation, which is eigenvalue depending parametrically on the frequency equal to the frequency. So if you think about the electron self-energy, we are doing something similar to find the quasi-particle eigenvalues for the electrons, okay? So this is just the transposition of the same concept for the phonons. To diagonalize this matrix, the issue we have is that this does not depend on the masses, but there are masses here, so that's not very convenient. So in the same way as in the FPT, we divide the force constants by the square root of the masses and then diagonalize. Also in this case, we take the phonon self-energy here, and we divide by the square root of the masses, okay? So that formally is equivalent to multiply this object by the square root of the 1 over the mass here on the left and on the right. So that's just a mathematical trick to make things a bit simpler. Now, this seems a little bit kind of obscure, but I would like just to tell you that this starts looking like a lot like the expression that Stefano De Girongoli gave you on the day 1, okay? So if you remember, you had the interatomic force constants divided by the square root of the masses, okay? And that was called the dynamical matrix. So here we're going to have something very similar, and this is, in fact, the many-body generalization of the DFPT dynamical matrix in practice, okay? So let me tell you how this relates to now density functional perturbation theory and why those two things are connected. The connection actually is very interesting. So this is the phonon self-energy. It's just the equation I gave you a couple of slides ago. And you recognize here that there is a frequency. So that's a little bit annoying because we are trying to look for phonon frequencies using an object which has also frequency dependence. Now, why the FPT is so much simpler and it's so neat, actually? Well, the reason being that in the FPT, we are not considering the fact that this screening depends on the frequency, okay? So let's consider a very simple example. For example, an insulator, so a semiconductor, with a band gap, let's say, of 2 volts or 3 volts. Or if you want, you can consider silicon, okay? So if you try to calculate the dielectric function, okay, and let's imagine that we're talking about the long range, so I mean the long wavelength dielectric function, so the macroscopic dielectric function. So in a standard semiconductor, it would have this kind of shape, right? So this is 0. This is epsilon infinity, if you want. And there is a resonance here at some excitation energies. So in the case of silicon, if you look at the dielectric function of silicon, so the real part, maybe this would be around maybe 4 electron volts, 3, 4 electron volts. But the most important bit is that if you go down to 0 frequency, actually, this function starts basically flattening out, okay? And as you can imagine, since this function describes vibrational excitations, probably at the end of the day, we will have to evaluate these functions for frequencies around the phonon frequencies, okay? So if I try to place the phonon frequency on this plot, probably I will be somewhere around here. So let's say in the case of silicon, this is 4 volts, and in the case of, so that's actually the main peak in the absorption spectrum, it's not the band gap. And the phonon energy, let's say the highest energy phonon is about 60 millivolt. So this is really far down. So at this point, one could say, instead of keeping a complete frequency dependence here, I could replace this function by its static approximation. So I say, well, I don't want to keep all of that. This information is a bit unnecessary, so I just work with the frequency here at omega equals 0, okay? And that's going to simplify my life. And maybe the approximation is not going to be too bad. And we'll see now that in some cases it can be quite bad, but in most cases it's okay. So if you do that, actually, you replace essentially this dynamic screening by some kind of form of static screening. That means I just take the self-energy at omega equals 0, and we call that the adiabatic self-energy, okay? Meaning that basically the electrons have all the time they want to adapt to the displacements. If you do that, actually, and you work out the maths, okay, so this is, I'm going to give you references about this, but if you work out the maths, actually, this adiabatic self-energy, so the one that is written here, so if you take that and you set omega equals 0, you can prove that that actually is mathematically equivalent to this expression. So that should remind you something, so that should ring a bell. So if you don't recognize anything there, we are in trouble. So does anybody feel something about that? I mean, do you use? No, nothing, okay. So this actually is almost identical to what Stefano De Gironcoli showed you on Monday, okay? So the only, let me maybe describe the terms. This is the second derivative of the electrostatic repulsion between nuclei, so bare nuclei. This is second derivative of the ionic potential, if you want, ionic pseudo potential with respect to the atomic coordinate times the electron density in the ground state. And this is first derivative of ionic potential times first derivative of the electron density, okay? Now, the little complication is that this electron density is not the one in DFT. This is the many-body electron density. So it's a very complicated object, okay? However, we cannot calculate that. Nobody has ever done it. So a simple approximation is to replace these two densities by the DFT density, okay? So you just say, okay, I don't know how to do that. I use the DFT electron density. If you do this operation, actually, this expression is identical to the second derivative of the DFT total energy with respect to the positions. In fact, the step to go from here to here is precisely the Hellman-Feynman theorem that Stefano mentioned on Monday, okay? So Stefano wanted to go from here to here using Hellman-Feynman. We can go the other way around, okay? So DFPT is solving precisely this problem, is looking at this dynamical matrix. And as you can see, this is a simple simplification of the many-body dynamical matrix. So there's a very clear connection between a many-body problem and the DFPT, okay? Now, clearly, this is telling us that DFPT is a adiabatic approximation. So we are replacing the dynamic screening of the electrons by a static approximation. And clearly, that works only whenever, whenever you are in this kind of region, okay? So I told you this is the example of an insulator. So one could say, well, wait a second, what happens for a metal? Well, technically speaking, in metals, you should not be using DFPT, okay, because it's not well defined. There is no adiabatic theorem there. However, in practice, the effects are not that big, so the differences, and therefore it works in many cases. So what we're going to see now is some cases where things don't work out. But before I proceed, let me just try to make the connection between the complete solution and the DFPT solution, okay? So this is the equation that we started from. So this is the phonon-Green's function equal mass omega squared minus the phonon self-energy. And I introduced the adiabatic approximation, which basically is replacing the complete self-energy by the zero frequency self-energy, okay? Using that, I can define a new Green's function, which is the adiabatic version of the Green's function. And now what I can do by looking at these two equations, maybe I can take the difference, so I can knock out these two terms, And if you do that, essentially I end up with the difference between these two. This is the exact solution. This is the adiabatic approximation, and the difference into two phonon self-energies here. So what we like to do is to call this difference essentially the non-adiabatic self-energy, meaning whatever else is left beyond the adiabatic approximation, okay? That's just a way to define this term. So if you rearrange these two terms, essentially you bring one on the right and then you invert, you find this equation, which is essentially something called a Dyson's equation for the full Green's function. So essentially it's full self-energy, full Green's function equal adiabatic one plus adiabatic self-energy full solution, okay? So you can imagine that can be solved by an iterative procedure, starting from these two terms and then upgrading this term and then keep going, okay? So that's basically a way to see this problem. Sorry. Yeah. So basically what I'm saying here is that, so this object is identical to that at omega equals 0. It's just, the definition is, so it's basically the same object but taking at omega equals 0. So the omega equals 0 is here, not here. So we are making an approximation on the self-energy, not on the equation for the Green's function.
Linked to this, you have done two approximations. One is omega setting omega to 0, the other is the density.
Yeah, that's correct. Yeah.
So which of these two approximations is the stronger?
Well, actually, we will see now that basically the important one is the adiabatic self-energy being replacing the full self-energy. For the electron density, we don't know because we cannot calculate the many-body electron density. I think what one could do is to look at how the DFT density depends on the functional and trying to see the effect of that. But that's essentially, let's say similar to saying how the phonon frequencies depend on the functional in a sense. So that is something that we can control separately, I suppose. Is that okay? Right. Yeah. Yeah. Yeah, actually, I will show you an equation for the self-energy. In fact, if you're wondering what the hell is that, so yesterday you have been calculating this non-adiabatic self-energy all along. So yesterday afternoon, when you were looking at the gamma of the phonons, that's basically, I'll show you in a second, that's the imaginary part of this object, okay? So that's basically the connection to what you've been doing. So it's not something, so that the kind of imaginary part of the phonon self-energy comes from this. I mean, there is no other way to obtain it. So that's basically just to say that now we have a connection between maybe, let's say, a DFPT result and a complete solution, and we can try to find out what it means in terms of calculations. So in the case of adiabatic calculations, the immersion of this equation is very simple because I can diagonalize the phonon self-energy, okay, and I get the phonon eigenmodes. So if I work in the basis of the eigenmodes, the self-energy takes a very simple form. It's basically a sum of two poles precisely sitting at the phonon frequencies, okay? So if you calculate these phonons using the FPT, for each phonon, you would have essentially these two poles looking like that along the real axis, positive and negative, and that's a very standard form for a boson Green's function. So that's let's say the adiabatic, let's say the FPT approximation. Then using this expression here, I can work out what happens if I go beyond that, and using the same representation, essentially, by doing a little bit of maths, actually it's quite simple to show that, you obtain the full Green's function, which is almost the same as this, but there is an extra bit, which is basically this non-adiabatic self-energy. So if I set this equal to 0, I recover this result only, which is let's say the DFPT Green's function. And if the self-energy is non-zero, I get something different. So if you remember yesterday's lecture, we had a very similar expression for the case of the electron Green's function and the electron spectral function. So we had, let's say, a DFT result, and then there was a self-energy at the denominator, which is changing things a little bit, okay? So that's exactly the same story, but for phonons. So this self-energy will change things a little bit. So in which way we can do a quasi-particle approximation like we did yesterday. This object is very complicated, but if we imagine that the spectral function will still be, so if you take the density of states of that, will still be some kind of peak, maybe a bit deformed, but still a peak, you can try to approximate this object as a single pole, and this pole may have a real part and a complex part. So it turns out that the real part is essentially the DFPT frequency plus a shift, which is the real part of the self-energy, and the imaginary part is essentially the imaginary part of the phonon self-energy. So the name of this object, gamma, is the same name that you had yesterday in the tutorial, okay? So what you were calculating yesterday is essentially this quantity. And the way to understand it is to go through these steps, okay? So why this is useful? Well, this is useful because if you do a DFPT calculation, maybe you get and you calculate the phonon density of states, maybe your phonon, suppose there's only one phonon in your system, you're gonna get a sharp peak, okay? That's a phonon which has an infinite lifetime because the broadening is 0. As soon as you switch on these effects, you acquire a shift in the real part of the pole, so that's a shift in the energy, so this thing has moved, okay? But also a broadening, so instead of having a sharp peak, this acquires a little bit of a width, and this width is the inverse of the lifetime of the phonon, okay? So when you're looking at a phonon lifetime coming from electron-phonon interaction, that comes from this kind of effects, all right? And that's something we can calculate now. That's quite straightforward. You've been doing it yesterday already. Let me show you a couple of details about the self-energy, and now it is implemented in EPW. So if you do the theory, and you rewrite these equations in a diagrammatic language, it turns out that the self-energy has a few components. So the matrix elements, the ones that we already talked about a lot. So this matrix element here, this here, 2 electron Green's functions, and the vertex, okay? So the only complication is that this is the matrix element of the FPT, and this actually is a bare matrix element, meaning that it is a matrix element which is not screened by the nuclei. I will say something more about that because it's a little bit complicated. But whenever you see 2 Green's functions like that in a loop, that essentially is what is called a polarization propagator. It's telling you that there is some kind of screening going on. And in fact, we say that there is a dielectric function appearing in the self-energy. And for completeness, I just want to show you that also the matrix element can be written in essentially a self-consistent equation, which involves, again, some kind of screening here. And this screening is what we calculate to some degree of approximation in DFT, okay? Now, the problem is that calculating the complete story is difficult. Nobody has ever done it. So what we do to proceed is something similar to the electrons. We kill the vertex because we don't know what to do with that, as simple as that. If somebody has any idea, let us know. And the other thing is that in the electron-phonon matrix element, we don't kill the vertex completely, but we replace it with the exchange and correlation DFT, okay? So for those who are experts in this area, maybe the language to use would be that the self-energy is calculated within the random phase approximation, okay, the Hartree screening, and the matrix element is calculated using random phase plus DFT exchange and correlation in the screening, okay? So that's actually what is being done in the codes, okay? The equations that you obtain, so if you translate this object into an equation, is this thing. So that's basically the phonon self-energy. You have seen this equation in the slides yesterday, and that's the equation which is implemented essentially in EPW. So it contains a bare matrix element, a screening matrix element, then there is some dynamical structure here. So you see there is a frequency dependence which appears in this denominator. So somebody earlier asked, how do we put the frequency dependence? It comes from this bit here. And the important thing is that this frequency dependence is next to some electronic energy scales. So these things really changes on the scale of electron volts, okay? So there is not much structure in the case of insulators. Clearly, there will be some structure in the case of metals, for example. The other thing I want to say is that, unfortunately, in the literature, for maybe 40 years, there has been some kind of slip, and essentially what we've been doing is to use, instead of the bare matrix element, essentially everybody has been using the screen matrix element. So essentially, instead of using 2 different objects, people have been using the same object here. And that actually is really what is implemented in EPW. So in a sense, in EPW, we don't have this guy, but we replace that by the standard FPT matrix element. That's a little bit of a mistake, but this is still really something that we don't understand very well. Actually, I guess there is more work needed in this direction. Let me see what happens now if I start taking this equation and applying to a couple of cases. In the case of the frequency shift, I need to take the real part of self-energy. So I just took the real part of what I showed you earlier. So why this is interesting? It is interesting because these are electron occupation factors. So if you think about it, suppose you have an insulator. if this is occupied and this is occupied, so 2 electrons in the valence, that's a 1 minus 1, so it's 0. If this is in the conduction, this is in the conduction, it's again 0 minus 0, so it's 0. So the only possibility when this is non-zero is this is the conduction, this is valence, or this is valence and this is conduction. So the only option for this quantity to be non-zero is that the two states belong to the two different manifolds, okay? Let's imagine that we're talking about an insulator with a band gap, okay? That means that the energies here, which are the energy difference between these two states, so these objects have to be at least as large as the band gap, okay? Because one belongs to conduction and one to valence. So that's at least the band gap. So here I have essentially 1 divided by band gap minus phonon frequency minus 1 divided band gap. So if the band gap, let's say, is 2 electron volts and the phonon frequency is 10 millivolt, this is going to be, if I do a Taylor expansion, this is going to be roughly 1 over 2 electron volts times 10 millivolts divided 2 electron volts. So it's a tiny quantity, okay? So this frequency shift, in the case of insulators with a good band gap and with small phonon frequencies, is essentially negligible. It's not 0, but is small, and in most applications in insulators it doesn't matter, okay? Or at least the experiments are not as refined as to resolve this kind of small features. Problem is that if you're looking, so this reasoning that I did holds for a finite band gap. If you now repeat the same reasoning for a metal, okay, the smallest excitation energy between occupied and unoccupied states is 0, because we have a Fermi surface, okay? So in that case, this number can be 0, or can be of the same order as the phonon frequency, so this object here can diverge, okay? Because we could have something which is, I don't know, 10 millivolt here minus 10 millivolt, so that's an infinity, all right? So there is actually the possibility that this quantity may be very large, and this can happen in metals, or it can happen in systems with a small gap, for example, graphene, or other systems with a tiny gap that you may have, you know, if you're looking at, I don't know, thermoelectrics or other, you know, very narrow bandgap semiconductors, this may be important. And to tell the truth, we don't know much about it because there are very few calculations around of this quantity, and you know, there is a lot to do still in this area.
Why is that prefactor not 0?
The prefactor, which one? Say again. So basically, if you are in a metal and so your state is here, and the other state is here, so it could be that this energy difference maybe, I don't know, is 10 millivolts. This is occupied, and this is unoccupied. So that prefactor is non-zero, because you know this is occupied. So this is F equal 1, and this is F equals 0. Let's say at 0 temperature. So this can be non-zero, but the energy difference may be very small, and it may happen that this energy difference resonates with the phonon energy. Okay, so that's basically right.
For the last term, could you say that we have to add this one to avoid the double counting?
That's correct. Yeah, that's precisely correct. So basically, this term is the point is if you do the maths, this term is already included in the DFPT calculation of the phonon energy, actually. So you are, so this essentially is the same thing, but in the adiabatic approximation. So you actually are canceling what was left out of the DFPT calculation. That's correct. Let me give you a couple of examples, maybe 3 examples on when things go wrong. So yesterday, I told you that we want to do many body approaches because sometimes something goes wrong. We cannot explain the experiment reasonably. So this was the example of gated graphene. Let me remind you, essentially, in this experiment, there is a monolayer of graphene on a substrate with a gate on top, and by changing the gate voltage, they managed to essentially raise or lower the Fermi level of graphene. So if you imagine the Dirac cone, essentially the filling of the cone changes with the gate voltage, okay? As this changes, the Raman spectrum, so which measures the highest optical mode, shows vibrational frequencies which change with the gate voltage, so with the electron filling. And I told you yesterday that if you do DFPT, so if you take a DFPT calculation, you do graphene, changing the Fermi level in your calculation, and you repeat the phonon calculation, your vibrational frequency is the red line. So there is no change with the gate voltage. Now, in this work, this is actually from the group of Francesco Mauri. What they did actually is to essentially use this phonon self-energy, okay, the shift of the frequencies coming from this non-adiabatic effects. And when they did that, they obtained this blue line, okay? So you can see that things are now in nice agreement with the experiment. So this is a case where these effects are important. So in this case, actually, they used a very nice visualization of what is going on, which actually is very appealing, and it goes a little bit beyond the maths. So what they basically, their interpretation is basically the following. If you have a Dirac cone which is filled up a little bit, and you have a vibrational mode, which is essentially the stretching of the carbon atoms, okay? In reciprocal space, this corresponds to doubling, essentially, the unit cell and moving the Dirac cones a little bit further away, okay? Now, if this displacement is dynamic, you can imagine a brilliant zone and the Dirac cones which are moving slowly, okay? In the adiabatic approximation, the electrons are always in the ground state, meaning that there is one Fermi level and all the electrons are sitting basically such a way as to fill all the states up to the Fermi level, okay? Problem is that in graphene, the phonons have, energy of 200 millivolts, so it's, they go very fast. So this means actually they are moving so fast that the electrons don't have time to relax to the ground state. So as you move the Dirac cone to the right, for example, in this example, if it goes too fast, the electrons that were here don't have time to relax and go here, so they stay here, and essentially the filling of the Dirac cone is changing, okay? So actually, I remember that they gave a talk at some point at a total energy workshop, I think here, and they demonstrated this concept very nicely because they showed a martini glass that, if you shake it very slowly, the level of martini stays the same, and if you go very fast, essentially it starts sloshing like that. So that's a bit the physics going on in this system, but really the actual calculation requires this non-adiabatic self-energy that I told you about. And this is a case where phonon frequencies are large enough that, they resonate with the electron dynamics, okay? That's the main point. So this is another example from the same group. This is essentially calcium intercalated graphite, so essentially layers of graphene with calcium in the middle. What they did here is the complete phonon dispersion. The black line is the phonons that you get from actually from Quantum-Espresso, the FPT. And if you switch on this non-adiabatic effect, the way I showed you earlier, you actually get the red lines. So there are bits in the brilliant zone where the difference between the adiabatic and non-adiabatic energies can be quite large, actually, okay? So typically, in the case of metals, these effects are concentrated around Q equals 0, so long wavelengths, and there is a reason for that, but we don't have time to go through this. But the main point is that in some cases, in delicate systems, maybe non-adiabatic effect will be important. So we cannot expect that the FPT will be okay for all systems, regardless whether they are insulators or metals. And this is an example actually from our group, a bit more recent, where what people did is to start from an insulator. So that's a very wide bandgap insulator, that's diamond. And they made it into a metal by bombarding it with boron. So basically, if you inject boron, boron has 3 electrons, diamond has 4. So essentially, you are removing electrons. And the effect is to lower the Fermi energy from the middle of the gap down into the valence, okay? So you create essentially a metal of holes in diamond. So what they did after that is to do inelastic excess scattering measurements. So in IXS, what they did is to measure the dispersions of diamond. So these are the phonons in the FPT. They measure basically this line, the red line, using inelastic excess scattering, and they obtain this spectral function, okay? So these are the complete experimental spectral functions. So this is the undoped diamond, okay, this object here. So that corresponds pretty much to this, what you calculate in the FPT. That's the calculation in the FPT. And if you start doping it, essentially, you have a softening at this point. So the phonon frequency here collapses a little bit, and that has to do with the presence of these holes in the system. And if you do a non-adiabatic calculation, essentially you can, so this is the calculation, you can capture this effect very well. And this is just a comparison between the experiment, the undoped system, the calculation including non-adiabatic effect, and what happens if you use the FPT straightforwardly. So if you don't do these corrections, essentially the FPT significantly overestimates the softening that you find in experiment. In fact, this is quite interesting because the way this experiment was performed is the following. After they discovered boron-doped diamond to superconduct in maybe 2004, there were some DFT calculations of phonon frequencies, and they found a giant softening, maybe, I don't remember, it was maybe 20 millivolt or something. And then people, after the calculation, some people went and tried to do the measurements using IXS, and in the measurement, the softening was much smaller, maybe 3 or 4 millivolts. And this discrepancy has lasted several years. So it took essentially, these non-adiabatic calculations to, reconciliate the experiments and the theory. So that's why these things may be useful in the future. Okay, there was a question.
Yes, you mentioned an example in which the density was not sufficient. My question is, how resolve an experiment like that? Having done the two kinds of calculation, how can you guess what the experiment?
Oh, you cannot guess it. I mean, basically, the FPT is the golden standard today. So that's the first point of call of what we can really do. I suppose that, that has been done for, a very large number of systems. So it kind of works well in most reasonable systems, okay? When the system gets more delicate, one has to do better, probably. But there is no systematics now. So actually, these things that I showed you are pretty much the only, there are maybe another 10 calculations of this kind, but we don't know much more than that. So ideally, you always want to include non-adiabatic effects, but that's expensive. That's why we don't do it regularly, if you see what I mean. So the other thing that you may want to consider, let's say to answer a bit more broadly. So here, this is a very good agreement with experiment, but we are really talking about smaller energies. So if you look at the complete dispersions, generally the dispersions of the system are okay. So we're talking about if you want to do measurements which really target specific vibrational modes and you want to be accurate, then you need to include these effects. But for example, if you're calculating phonons to, study heat capacity or properties which depend on an average of the phonon density of states, that should not be affected too much. So that's why most of the things that have been done so far, they work quite well, actually. Okay? So it's mostly to address very specific experiments, like this one, like the one on Raman on graphene and things like that, that we need to be careful, okay? But I agree, essentially, more systematics are needed, essentially. And hopefully, this thing will become more popular in the future, and we will know a bit better when this is the case and when this is not. Just to connect with what you did yesterday, if we take the same self-energy and we try to get the lifetimes, so that's the imaginary part of the self-energy. So if you take the imaginary part of what I gave you earlier, that's basically the same expression with two matrix elements, this factor here, and then the imaginary part of this 1 over frequencies transforms into a delta function. So also here we can do some interesting reasoning. For example, this delta function says that this is non-zero only when the k plus q state is at an energy which is the energy of the k state plus the phonon energy. So if this is k plus q has to be above it, okay? But if you remember this factor here, I told you that one has to be occupied and one has to be empty. So essentially, one is below, one is above, and one has to be occupied and one empty. That means that the only option is that they are basically they are differed by a phonon energy because there is this delta function, but they are across a band gap essentially. So this means that if you look at a system like an insulator, so this term will always be 0 if the band gap is larger than the largest phonon energy, because it is not possible to connect two states across the band gap and satisfy at the same time all these conditions, okay? That means that if your largest phonon energy is 100 millivolt, for example, and your band gap is larger than 100 millivolt, there is no phonon self-energy, so there is no broadening of the phonon lines coming from electron-phonon interactions. So clearly there could be some anharmonic broadening, but that's another story. If you are in a metal, things are a bit different because if you are just near the Fermi level, so electrons below the Fermi level can make a transition to states above the Fermi level, okay? And that can happen in many metals, and that's why you have essentially finite broadening in metals, and we have seen the example, I think, of lead in the tutorials. So this effect of phonon broadening essentially happens either in metals or in very low bandgap semiconductors or in zero gap systems, okay? So in other systems, you don't have this kind of effect. You only have the anharmonic phonon lifetimes. And just to connect, maybe I'm gonna close after this slide, to connect with what you've seen yesterday. Somebody asked me, why we use this expression, which is the double delta approximation for gamma. Well, the answer is because that's something that's been done for 50 years. This is an approximation to the expressions I gave you earlier, and the approximation is very brutal. So essentially, it's so if you go back here, essentially what we do is to expand this. Essentially, we use this delta function to say that the Fermi Dirac at the energy k plus q is equal to the Fermi Dirac at the energy k plus a derivative times the difference in energy. And then we say that the phonon frequency can be neglected. So this is a diabatic approximation of the non-adiabatic self-energy. So you can see that this is getting dodgy. But that's something that people like. And the reason why this has been used is because this function is actually numerically very stable. So if you replace that by a Lorentzian, that's by a Lorentzian, that's always a positive number, so you don't get weird things. It can be calculated quite easily. So that's actually what is implemented in Quantum-Espresso, apart from EPW, and is also implemented in EPW. So that's something that you can calculate. However, I think one has to use a lot of caution. This is a brutal approximation, and actually in some cases it's completely pathological. Let me maybe make an example. So if you see these two Dirac delta functions, okay? So let's say this state is on the Fermi surface, this state is on the Fermi surface. So the integral essentially counts how many ways you have to connect the Fermi surface by a phonon wave vector. So if you have a Fermi surface and you want to count how many ways you have to connect it using a wave vector, the problem is equivalent essentially to finding the intersection between two Fermi surfaces displaced by a phonon, okay? So if you have two spheres displaced by a wave vector, the intersection is a circle. If you go to q equals 0, the circle degenerates into a sphere because they overlap, and essentially this expression blows up. So if you do a calculation of gamma, that's infinity. That's clearly wrong, but that's the approximation, okay? So if you can do better than that, try to do better and try not to use this. But if you're desperate, I think that's the first point of call. I guess that's how it goes. I mean, there is no reason, so there is no physical reason to use this, apart from the fact that, you know, in the 70s where people introduced these things, that was the only thing possible. Today we have much more powerful computers, so probably we should avoid these things. Finally, just an example of calculations. So in this calculation, that's again the group of Mauri. What they did is to look at IXS spectrum. So these are the phonon peaks from the spectra, and the width is the broadening. So this is the calculated broadening, the red rhombi, and the black things are the experiments. So you can see that these calculations can get quite well the experimental broadening, so that's quite nice. And that's pretty much it. So we skip these two slides because I think it's a bit technical. And you have seen already the polar matrix element yesterday from Carla and Samuel, so there is no need to talk about that. But I guess the bottom line is that I hope that, you know, apart from the maths and apart from the fact that, you know, these equations are a bit painful, I hope that I managed to convey the message that, you know, there is no ambiguity about how we need to work, work out electron-phonon physics. So the maths are there. They're a bit difficult, but everything is completely rigorous and completely robust, okay? So then what happens is that we need to make approximation to do practical calculations, and typically we use DFT, but the starting point is extremely robust, and there is no basically question on what we should do and how, all right? So everything else that you see is just approximations dictated by necessity of not spending too many compute hours. But the theory exists and is quite established now. Okay, I guess that's the end of the story. And if you're interested in the equations, basically in the middle of this review, I mean, you find all the equations derived one by one. But most importantly, if you are brave enough, meaning that you feel very energetic, you can try to read this paper. I mean, I can tell you that's very painful, but it's amazing. Actually, actually I think it's called something like a quantum field theory for solid state. So you can imagine that, you know, it's going to be 30 pages of maths, but it's really beautiful because it has pretty much everything that we need, okay? It's just a slightly old language, so it's a bit painful to go through this kind of old formalism, but it has pretty much everything. So if you, at some point, you have any doubts, that basically has all the answers, okay? Okay, that's the end of the story. And if you have any questions, just maybe we have time for one question before we move to the next lecture.